Hey, I'm Ryan Kooiman, Director of Training with Standard Motor Products, and welcome to this month's Power Hour. Today we're going to be talking about wheel speed sensor and more importantly about diagnosing them. Now they've changed throughout the years. I don't know if you've noticed, but the way they used to be more of an AC generator, they've now moved to a square wave, Hall effect, magneto-resistive type sensor. And so yes, our diagnosis is going to be a little different. Unless you've always been rolling the dice and just, follow the code, that might still work for you. But let's get a little bit more into the specifics of the diagnosis and how those sensors work. Let's start. All right, well, let's get started. As mentioned, today's topic is modern wheel speed sensor diagnostics. So as we look at the overall ABS system or the traction control system, there's a lot involved here, and they're all networked together. So we've got wheel speed sensors, typically at each wheel. We've got the brake switch, we've got the PCM, we've got the brake master cylinder, electronic brake control module, the instrument cluster. And they're all going to be networked together, talking on different networks on the vehicle, depending on the vehicle you're working on here. So, this is our opportunity to get into network diagnostics as well. I'm not going to cover that today. We'll maybe save that for a later topic. But my point here is there's a lot going into the ABS input here. Traction control, keeping the driver safe. So the heart and soul, and what we're really going to be talking about here today, is wheel speed sensors. This is the input from each individual wheel going to the ABS controller or the electronic brake control module, whatever your particular manufacturer is going to call it. And so this is going to be our key inputs here. Now, these things have changed over the years. So I'm going to use the term passive wheel speed sensor. And this is kind of a legacy system, or this is what most of us have grown up seeing. So quite often, we'd see a wheel speed sensor sticking through the hub on a vehicle and reading a tone ring off a CV axle, or perhaps something installed in the wheel bearing like this. And so a lot of these were going to be passive style wheel speed sensors. And so the way that this works, this is a variable reluctance type sensor, and this is going to be an AC generating sensor. So as you can see here, we've got a permanent pole with a magnetic field around it. And so as these tone rings are going to go past the sensor, it's going to output an AC signal. And so as the speed increases, the frequency will increase as well as the amplitude here. So higher amplitude typically indicates higher wheel speed. So how do technicians test this? Well, one of the simplest methods is to use the DVOM, digital voltage ohm meter, and test the resistance of the circuit. So let's say we've got a trouble code for a left front wheel speed sensor. Well, we can go in and monitor the resistance of that particular sensor and compare it to a known good. Well, what's our known good? Well, hopefully the right front will be working just fine. Now, there's some problems with testing the resistance of a circuit. I can, if you check my heart rate and I'm sitting in a chair, it's going to be perfectly fine. But if you ask me to go run around the building, especially here, we're having a warm day in Texas right now, it's going to actually increase and be significantly different than what we had before. So keep that in mind if you're doing any type of resistance testing, that your results may vary. And so bad is bad, but good might be okay at this moment. And so what I mean by that is sometimes testing resistance, we want to actually move the harness. Keep in mind, a lot of these wheel speed sensors have a pigtail, and there's a lot of movement in this. This is tied to quite often the strut or one of the front steering knuckles. And so every time the vehicle turns, it's going to flex that harness. Every time the suspension goes up and down, it's going to flex that harness as well. Not so much variation in the rear, but typically in the front, we're going to see a lot of movement on those harnesses. So it's a good idea to manipulate those harnesses also while you're checking the resistance here. Another method is to test the AC output. So in this image here, you can see we're just the two leads across the two wires on the ABS sensor here. and we're monitoring the AC voltage, not the DC, but the AC, and then have an assistant rotate the wheel. Or if you can do all this yourself, more power to you. But as it rotates, we're going to see an AC signal increase there. And so that kind of gets us in the ballpark. Let's know, yes, it's working. No, it's not working. However, a more accurate way to do it is by using a lab scope. And so I understand not everybody's going to have a lab scope, or people have a lab scope and they're maybe not familiar with it. Well, it's a good opportunity if you're that person to pull it out, play with it after work, maybe on Saturday, something like that, and get familiar with testing different sensors on the vehicle. So in this particular one here, you can see my scope setups. And so, yeah, I could back probe it with it connected, but in this case, we're going to check an AC signal. And again, these things are self-exciting, if you will, or self-generating, so they do not require a DC voltage input. Later, we'll talk about new sensors, and they're going to require a DC voltage input. However, these ones here, you can simply have it unplugged, like this one I've got sitting here in the cart, and you can read across it. And now as we rotate it, the scope is going to give a signal like this. Now, I got to be honest with you, this capture was not recorded solely from this setup here. You can see here I'm going directly at the sensor. On this particular one, and this is one of my tech tips, come from many years of experience, I'm going to go directly to the electronic brake control module. And I'll call that my one-stop shopping. Now, quite often this is going to be located maybe on the driver's side under the hood near the brake master cylinder. And so what I can do is, using a wire schematic, I can look at my left front, my right front, my rears, and determine which sensors I want to test. So in this particular vehicle, if I suspect one of them and then install it with my known good, I can compare the two. So if we take a look closer at my pattern here, you can see that the frequency is the same, right? And so both wheels are in phase as we're going straight ahead. Now keep in mind, if you go to the left or right, it's going to change it, because the outer wheel is going to be traveling faster than the inner wheel. But one thing you'll notice here is my peak-to-peak voltages on the blue one are higher and lower. We've got greater amplitude on the blue channel than we did on the red channel here. And so what that's going to do, it's going to indicate a stronger signal from this particular one. And so while the frequency is the same, their phase the same, amplitude is different, and that's enough for the electronic brake control module, or the ABS module, to determine that this wheel is traveling faster than the other one there. And so that's where we run into false ABS activation or stuff like that. Because if it thinks that this one is lower or maybe locking up, it's going to release the brake pressure to that particular wheel. And so, being from Michigan, spending most of my career as a technician working in the Rust Belt, this is a very common sight for us. You know, quite often we be working on these things and we get so much rust buildup on the surface of the bearing hub or the steering knuckle, it would move that sensor further away from the tone ring. And so we would get a different amplitude from that particular one. So in this scenario here, we're going to plug this hole off, make sure we don't get debris down inside of there. And then we're going to clean this surface here, the mounting surface, before installing our new sensor. And so that's one of my other tech tips here for you today. Make sure you've got a good clean mounting surface. Because if you mount a new sensor on there with a rust, it's going to be further away in proximity than perhaps one of the other sensors there. So that's it for the older style system. But now the newer style sensors are going to be referred to as active speed sensors. Now there's a couple different variations of them, but at the end of the day, they're very similar here. And so some of these actually started around the year 2000, but personally, my first experience was in 2010, a 2010 Chevy Equinox. So let's look at a little bit into what goes into these. These are going to be either Hall effect or magneto-resistive type sensors here. So Hall effect sensors are most commonly used in the automotive applications for measuring the speed of a rotating object like a crank or camshaft. They really gained popularity as wheel speed sensors because of their accuracy across the entire speed range along with their resistance to dirt, mud, water, all the other good stuff you find in the inner wheel wells or near the wheels on most vehicles. So unlike the magnetic generator type sensors or the AC signal generators, these Hall sensors are going to produce a very accurate square wave signal. So the sensor is constructed of a stationary permanent magnet and a semiconductor Hall effect chip that will be mounted right next to each other and separated by an air gap. Now, a metal rotor consisting of some windows and tabs is mounted to a shaft, such as a wheel bearing, as you can kind of see in this image here. And so during rotation, the windows and tabs will pass this permanent magnet and the semiconductor Hall chip. This effectively shields and exposes the Hall chip to the permanent magnet's field based on whether the tab or window is actually there. When the shutter blade or the tab is blocking the chip from the magnetic force, a voltage will be produced from that sensor. When the chip is exposed to the magnet or the window, the voltage is going to collapse here. And so the magnetoresistive sensor is very similar to a VR sensor with Hall effect-like properties. And so that's what we're going to see probably the most often here on ABS applications. So this magnetoresistive sensor is going to require a power source. So that's kind of different than what we talked about previously as well. And so, that MRE sensor will have the power source and produce a frequency modulated signal. So this is a very accurate way to analyze rotational and linear position by measuring the direction of the field lines, not necessarily the magnetic strength. So these sensors are becoming very popular in automotive applications due to their accuracy and adaptability. And so we're seeing magnetoresistive sensors used in ABS, cam, crank, where a lot of Hall effect sensors were used. We're now seeing the MRE here. And so when it comes down to it, with these MRE type sensors here, we're going to be able to measure the voltage. First off, we have to make sure that there's voltage present, and then we're going to be testing the voltage through the whole unit. So as we take a look at a schematic here, this is from a Chevy Equinox. We've got all 4 wheel speeds here. And then we've got the sensors. We can see the image of the tone ring. But then as we look down here, we've got a ground, and then we've got B+ being applied to it. And then that's going to be our signal, which will be tracked through there. So here I am using a lab scope. And so this is, in many applications, only a 1 to 1.5 volt pattern here. But we can see we've got our square wave pattern on this particular one. Now here's looking at a schematic from a Jeep Grand Cherokee here. We've got all 4 wheel speeds again, and they display it a little different. They show a sensor supply and a sensor ground signal. Remember at the beginning of the section, I said there's going to be 2 different styles. So this is the first style, and now here's the second style. And it's going to really do the exact same thing. So I don't want to confuse you or go into those details on that particular part, but just understand these newer active style sensors are going to be outputting a square wave signal, much different than what we're used to seeing the AC sine wave. Now, how do we know which is which? I think it's fair to say any 2010 or newer vehicle is going to be one of these square wave output type sensors, much more accurate and much more precise. So with our diagnostic process, first off, we want to make sure that we've got B+ present. So I'm using my DVOM here again to make sure that we've got voltage present. And so, whereas previously I was going to disconnect the sensor and put my meter across here and see what kind of AC voltage it would produce, we need to keep these plugged in. So you can see I'm back probing here, because remember we have to have that 12 volts going to it. And so I'm going to back probe to it and rotate. And so I should see some change on my meter there. I'm not going to be able to see a true square wave, but I will see fluctuations on the voltage reading on my meter, checking in the DC setting. Remember previously we were in the AC setting. On these sensors, we're now in the DC setting. So we'll see that voltage actually change there. But again, there's really nothing more accurate than using a lab scope here. It's going to draw us a picture showing us voltage over time. So you can kind of see the setup I've got here, looking at a Chrysler. And so you can see as we begin rotating the wheel, we've got our square wave, but it's spread out. So as we rotate the wheel faster and faster, we can see that it's occurring much quicker and quicker. We don't have an amplitude change like what we had previously on the old style sensors, but they're just occurring more quickly here. And so hopefully this is a good visual representation for you there. Now, if you look online and get in some of the industry chat rooms, for years people have talked about testing the current on these. And so yes, I've done that many a times, but it requires the use of a micro amp probe. So we've got our high amp current probe, going to be used for like relative compression, starter testing, etc. Our low amp current probe, which we will test like injectors and some sensors, maybe ignition coils, etc. But then this is a separate micro amp probe, which reads much smaller levels. It's going to output a voltage to the lab scope here. It's available. And so this is the type of pattern you're going to see. Again, it's going to produce a square wave here. It's going to alternate a very small current there. My humble but probably accurate opinion, just stick to voltage. I've never seen anything more using this microamp current probe than what I saw by looking at the voltage pattern. So if you're a scope guy, maybe save yourself some money and don't go down this path. If you'd like to, though, feel free. It's worth a learning exercise there. So one question I know is going to come up, can I use my meter to check resistance? Absolutely. And so once again, I strongly recommend checking the resistance and comparing it to the suspected bad side and compare it to a known good, hopefully on the other side there. And so one thing is we have to pay attention to the polarity. Now you can look at a wire schematic. I'm never going to discourage you from looking at a wire schematic to determine which wire is which, but we've got a 50-50 shot here, right? And so we're going to test the polarity, we're going to, or excuse me, the continuity or the resistance of this particular sensor. We're going to disconnect it, unplug it from the vehicle. I don't care about that voltage going to it right now. And so we're going to put our meter leads across. Now, if you get it wrong, it's going to read open circuit or the OL, which is seen here. Then quite often I'll look at that and go, oops, I got it wrong. I'll switch my leads and retest it and then get my resistance reading. If it's OL on both sides, well, it sounds like you found your problem there. That's where our problem sensor is. So hopefully you understand a little bit about how we can use our meter to still pinpoint where our problem is here. So let's take a look at a broken vehicle here. Now this is a Jeep Commander 4.7 liter. Customer's concern is false ABS activation. And so on these older vehicles, you know, again, growing up in the Rust Belt, this is a very common concern. Quite often I would drive the vehicle in a safe environment, like the shop parking lot, and look at my scan data, graph all four wheel speeds, and see which one dropped out. Now, quite often, remember the old ones, it's AC signal generating. So it's going to be weakest at the lowest point. And so a lot of those, you would start ramping up or you'd start accelerating, and you get about 3-4 miles an hour. 2 or 3 of them would be showing, and 1, maybe 2 would still be stuck at 0. Well, as you get up to 10 miles an hour, they all start working and reading properly. So that's how I personally used to diagnose false ABS activations on older vehicles with a passive style sensor. So how are we going to do it on a newer vehicle here with active style sensors? So got the work order here. It says ABS warning lamp is on, which is a good thing for us, right? And false ABS activation. So plug in the scan tool here. I'm using the factory scan tool at this time. That's what I had with me. And so using the Chrysler Y-Tech, you know, we could be using one of many aftermarket scan tools here to get a lot of this information. But we can see we got a couple different trouble codes and different modules. I'm not too worried about some of the other ones, but we can see in the ABS module here, I've got a C1015, which is an active code for right front wheel speed sensor circuit. Okay, well, so if we're going to do the code reader, you know, parts canon, let's just order a right front speed sensor. In this case, you're probably going to be successful with that. But we like to go a little bit further and verify it. So as I'm going to test drive the vehicle here and look at the data, like I've always done, you can see I've got wheel speed sensors here, and then I've got wheel speed sensor information down here. Well, why are they listed twice? Now, if we go over further, we can see the unit. And so we've got RPM on the top ones here, and then miles per hour shown later on. And so that might be unique to some of you. You might not be familiar with seeing both RPM and miles per hour shown. So if we look at the mile per hour section down here, we can see they're all roughly showing just over 10.5 miles per hour. And so that's pretty consistent across the board. However, if we look at the RPM values, we've got one reading 122.5 RPM. We've got the right front, which is where our trouble code was set, right? Reading 3F space FF, which is kind of a failure message. And then we've got the other ones reading 123 and 123. So what might look normal or kind of an inferred value on the miles per hour could really leave us scratching our head. However, if you look at the RPM, now it's going to help us pinpoint here. So that's one thing I want you to be aware of and take a look at next time you're driving a newer vehicle. See if it offers wheel speed in RPM as well as in miles per hour. We've all got plenty of horror stories of when a scan tool or the control module made up data and gave us an inferred value there, which would be displayed on that. So my point here is look at more than just the miles per hour. So in this scenario, I'm always going to graph the data. A picture's worth 1,000 words, right? And so the older I get, yes, I need my glasses, but it's harder to concentrate while driving the vehicle, illegal in many states too. But as you're looking at those numbers fluctuate, it's hard to pinpoint where abnormality is. So by graphing it, we can see consistency here. And so if you look at where my cursor is, you can see each wheel is going to read relatively close to each other. And so by just looking at this, I'm like, what's going on with this? Everything seems to be okay. But now as I move my cursor just a little bit further, notice that the right front disappeared. So if I go back to my previous screen, I've got all four. And then I move the cursor a little bit further, it doesn't drop off. I don't see a line like I was kind of anticipating here. It just disappeared at this point. And so that's another tip for you. Be aware of this type of stuff. And the worst case scenario is when you're learning about this on a broken car, especially if it's at 4:30 on a Friday afternoon, right? So that's why you're paying attention to some of this training. You're learning about this, but I don't want this to be the first time you're seeing it when you're testing a customer's vehicle. Now, as I broke those graphed wheel speeds apart, instead of having them overlaid, I separated. And so we can see one of them here, but we can see our right front all of a sudden just disappears. Once more, I was kind of expecting it to drop out and see a line go this way, but it just disappeared. And so that is not the first time I've seen it, and I've seen it many, many more since then. So be aware of that. So at this point, we're going to a simple ohm check or resistance check of each one. That right front was significantly out of range. So now we've got a trouble code. We've got wheel speed data, which is indicating a fault with the right front. And then we've got a resistance reading pinpointing that we've got a faulty sensor. So I've gone ahead and replaced the right front sensor. And as we drive the vehicle again, everything's all in sync. No more dropouts, no more warning lamp. And so really a very straightforward diagnosis here. However, it's a different style system. The data looked a little different than what we were expecting in this particular one. So, really my summary is ABS lamp was on. Mile per hour did not drop out, but the RPM did drop out. So make sure you understand what your scanner is truly reporting on that. So as I'm kind of wrapping up here, I want to bring one more application of wheel speed sensors to light, and that's hill start assist. And so we've seen this on newer vehicles past 15, 20 years probably. And so that's when somebody's sitting on a hill and they apply the brakes, and then they want to move their foot from the brake pedal to the accelerator. The vehicle will detect that it's on a hill, and it will hold the brakes until the throttle is applied, and then it's going to release the brakes and go forward. You know, this would have been nice back in the day. I had a Camaro stick shift on my way to college. There was a red light on a pretty significant hill. So I got really good at balancing and not burning out a clutch there to go in between the two. So hill start assist would have been a fantastic thing back in the day. So vehicles use a different combination of sensors, maybe a yaw sensor or a pitch sensor, but many vehicles will also incorporate the ABS system into it. And so if it detects a reverse rotation, it will apply the brakes, especially with the vehicles in the forward motion, or the forward gear. Especially I've got a Toyota here in the shop. We've got a Prius sitting in here as well. And so Toyota is one of the main manufacturers that relies on wheel speed sensors for reverse rotation detection. So that's one thing I want to bring up here. These are not all created equal. And so we found this out the hard way with different customers. You know, as many that have been watching these sessions for a long time know, the backside of the wall here, we've got our vehicle test facility where we validate all these different products. And so we can see here's our unit on this side. You notice it's a complete chip. One of the competitors almost looks like a mass airflow sensor here. And so just by simply looking at these internals, now we had to carefully remove the outer casing here. But if you look at these things, there's significant difference in technology on the chip on this one versus this one. And what we found with some less reputable or inexpensive options on the market, they do not detect reverse rotation. And so that's important for you to know and validate your part source here. So what I mean by that, by looking at one of ours here, we can see as we're going forward rotation, it's our traditional square wave signal here. Then we stop the rotation and we start turning the tire backwards. Look at, we've got this kickback signal here. And so this indicates to the control module that the wheel is in reverse rotation. Now by comparison, this is a test we did with a competitor's sensor on the exact same vehicle. We verified with the OE sensor, we verified with our sensor, and then we used one of the competitors. And you notice the forward rotation, we stop, we start to go reverse rotation here, and we don't see those spikes. And so it's not reporting back to the vehicle that the vehicle is in fact rolling backwards. And quite often you're going to get a VSC error, maybe an ABS error, traction control. You know, in these Toyotas, you get one fault, it lights up the entire dash. But more importantly, the hill start assist might not be working properly. So keep that in mind next time you're looking for an ABS sensor. So as we kind of wrap things up here, you know, a couple of key takeaways. Hopefully now you have a better understanding of the ABS fundamentals and how the wheel speed sensors are incorporated into that. Hopefully now you have a better understanding of how to test an active style wheel speed sensor. At the end of the day, we hope that you make an accurate diagnosis and a proper repair to keep the customer happy and keep your business profitable. If you're looking for more information on this, you can always go to our YouTube channel and just type in ABS. We got more information about our program there, about our sensors, different diagnosis. We've done a couple different power hours on ABS systems already. You can find all that stuff on our YouTube channel. And then if you go to standardbrand.com and under the keyword search there, just type in ABS and you will see multiple articles, catalog lookups, just a lot of great information there to help you understand what you're working on. So that's it. I'm going to turn it over to Corey now. I see there's been a couple questions. He's been answering some of them, but you know, he always brings a couple of good ones for me here.
Yeah, and I'm going to go directly to the last one I got because it was back to your last point you were making there. The question came through from Brian. Is there a way to visually tell which of the sensors have that reverse rotation sensing you were just talking about?
Great question, Brian. And unfortunately, I've not been able to figure it out. We've done our work to pull this off, but quite often you look at this from the outside, they look very, very similar. So, good question. Unfortunately, I don't have a great answer for that. So, kind of goes back to validating and following the reputation of your part supplier, your manufacturer that you use there. Again, we're not afraid to show how we test them and show the results. So,
all right. And then we got Keith came in and just wanted to know: do all the vehicles now have 4 wheel speed sensors? Are they all independent now?
I would say most newer vehicles do. In training, we never say always or never because somebody will always pop up, and I'm sure somebody will type in. But most vehicles, today's modern vehicles, are going to have a wheel speed sensor at each individual wheel. Now, there's been years where I've seen some of the, like Hyundai or Kia, might only have one rear wheel speed sensor because they're paying attention to the front ones as they're turning and the power is being delivered to it. And so it might only use one in the rear. Some other vehicles, here's a vehicle speed sensor off of Ford. It'll have sensors in the front wheels and then just one in the rear axle, but that's an older application. So I would say probably 99.8% of the new ones are going to have a wheel speed sensor at each individual wheel.
All right. And I'll throw one more at you, Ryan, because Leo had a question I think a lot of people probably have as well. A lot of the older sensors used to read off a tone ring on the axle, but he doesn't see that much anymore these days. So how's this sensor actually reading? Yeah,
great question, Leo. So a lot of the old ones, we'd have the axle going through here, it'd have the tone ring in it. I love those again because quite often they'd have a chip in it or they'd split off, and pretty easy money to make there. The newer ones, we're going to see it in a bearing here for the most part, and it's kind of almost a tape that's inside of the bearing. And so on some of these things, you pop the actual bearing out, it's built into the bearing, not so much into the hub. And so it's a very thin surface there that's got that the magnetic window and the tab to basically indicate as it goes past the sensor. We can't visibly see it. It's inside the bearing itself, but it's still there. And so, yes, it's not as visible as it once was, but it's definitely there. Much more reliable, right? And so I think we see less failures in that regards as we did on the vehicles in the late 90s, early 2000s. So thanks, Corey, for being my great producer here. And thanks to all of you for coming in. We look forward to seeing you at the next Power Hour. And we'll actually be talking about air conditioning. 'Tis the season.